Hello, everyone. So far, we have considered real coefficients of a polynomial function. When we uh, talk about polynomial functions, we consider this an or the coefficients to be real numbers, but that's not always the case because we may have or we can have imaginary coefficients, and also the values of x could be imaginary. So x can take imaginary numbers. Now let's generalize the polynomial function uh, that we know to more general form, which is complex polynomials. So when this coefficients an minus 1, and so on, if they can take a value, an imaginary value, then we call this polynomial function a complex polynomial. Now, for example, just like the real polynomial, we can of course find the zeros of a polynomial, complex polynomial. For example, we can take this g of x, which is given by this, and determine if this c equals to 6 minus I, where I is the imaginary number, is a zero of the polynomial or not. Okay, we wanted to know if this is a zero of this polynomial. And now, how do we know that if it is a zero of the polynomial? Well, we will use the remainder theorem. So we will divide this by this factor, and well, if f of c is r, then that means it's a factor. Okay. Okay. So I will use the synthetic division. So we have RC is 6 minus I, and the coefficients are 1, minus 11, 25, and 37. So we pull this down and we multiply this, we get 6 minus I. If we add this, we have 5 minus I, and then this times this, it will be 30 minus 6I minus 5I plus 1, so it will be 31 minus 11I. If we add this, we get 56 minus 11I, and then okay, so if we add this two up, we get minus 5 minus I, and then multiplying this by this one, we get minus 31 minus I. And again, if we add these two numbers, 25 plus this number, we only add the real part. So we get minus 6 minus I. Then 6 minus I times minus 6 minus I, it will be negative 37. And the remainder is 0. And as you can see, using the remainder theorem, f of c, which is f of 6 minus I, is r, where r is 0. So basically, f of 6 minus I is 0. And what does this tell us? Well, the function at x equals to 6 minus I is 0, which means this number is a 0 of the polynomial function f. Therefore, the answer to this one is yes, this is a 0 of the polynomial f. Okay. All right, and the next one, the next theorem is the factor theorem, and this one tells us that if f of c equals to 0, then x minus c is a factor of f of x. And the other way, if x minus c is a factor, then f of c is 0, which basically is what we got here. Okay, so here we have c, and we found f of c to be 0. Therefore, since f of c is 0, then the factor x minus 6 minus I, well, this is our number in this case, this is a factor to the function, to the polynomial, okay? And if we know this is a factor, then f of 6 minus I is 0, okay? It goes both ways, both directions. So this is basically what the factor theorem is saying. Now let's use the factor theorem to determine if the given binomial is a factor of f of x. So here we have the polynomial function, and here we have the binomial factor. Well, we don't know if it is a factor or not, but we wanted to check if this is a factor. Now, how do we check? Well, we need to divide the function. We need to divide f of x by x minus 5, sorry, plus 5. And if the remainder is 0, which means if f of c, which is in this case is minus 5, if this is 0, then x plus 5 is a factor of the polynomial. Now, what is c in this case? Well, c is minus 5, because x plus 5 means x minus 5. Okay? Therefore, this is our c. Therefore, here we have our c, and these are the coefficients: 1, 11, 41, 61, and 30. And we pull this one down here, then minus 5 times 1, negative 5. We add them, positive 6. Negative 5 times 6, negative 30. We add them, we get 11. Negative 5 times 11, negative 55. And we add 6. And negative 5 times 6 is negative 30. And when we add them, we get 0. So the remainder is 0, which means when we divide this function by x plus 5, the remainder is 0. Okay, therefore x plus 5 is a factor of f of x. And similarly, we can divide f, the function, by x minus 2. In this case, our c is positive 2. And if we follow the same procedure, the remainder will be this number, which is not 0. Okay, so since this is not 0, by the remainder theorem, well, this is not a factor. X minus 2 is not a factor of the polynomial function. Now let's factorize this function given 1 over 4 is a 0 of the function. Now we have this information. 1 over 4 is a 0 of the polynomial function. Now, what do we know using the by the factor theorem? If 1 over 4 is a 0, then x minus 1 over 4 is a factor. Okay, therefore we can divide this function by this factor, and the remainder will be 0. So let's divide this and try to find the other component. All right, so using the syntactic theorem, syntactic method, I will have 1 over 4, and the coefficients are, then I will have this 20. So this 1 times this, it will be 5. If I add this 2, we get 44. 1 over 4 times 44 will be 11. If we add them, we get 8. This is 2, and the remainder is 0. Now, the important thing here is it's not the remainder, because we expect the remainder to be 0. We knew the remainder is going to be 0 because 1 over 4 is 0 of the function. Okay, therefore the remainder is always 0 if the number is a 0. But the quotient has these coefficients. Okay, when we divide this function by x minus 1 over 4, this is the quotient. So I can write f as x minus 1/4 times this polynomial with these coefficients, 20 times x squared plus 44 times x plus 8. We can factor out 4 from here to make it easier. I will bring 4 here, x minus 1 over 4. And here we have 5x squared plus 11x plus 2. Okay. Now, as you can see, using this information, we reduced our function, our polynomial function, in this form. It was difficult to factorize this one, but now it's easier to factorize this because we pull out one factor, x minus 4 minus 1 over 4, and the remaining part, well, it's a quadratic function, quadratic expression. So we can factorize this one. If not, we can use the quadratic formula to find the zeros of this function, okay, this expression. Therefore, to factorize this one, we have 5x squared plus 11x plus 2. And well, we know how to factorize this one. So this is 5x squared plus 10x plus x plus 2. Okay, the two numbers whose sum is 11 and product is 5 times 2, which is 10, are 10 and 11. Okay, so from this we have 5x plus 1 and x plus 2. Therefore, the function f of x is factorized as 4 times x minus 1 over 4. And then we have 5x plus 1 and x plus 2. Okay, so this is the factorized form of this function or this polynomial. Okay, and here the other way, write a polynomial f of x that is of degree 3 with zeros, -2, 3i, and -3i. So for a polynomial of degree 3, we expect, or we know it has 3 factors, okay, including multiplicity, I mean, because there are the degree 3, we multiply 3 different factors to get degree 3. And already we have 3 of them, okay? This is one factor, this is 1, 0, another 0, and so on. So the factor corresponding to this one is x plus 2. The factor corresponding to this one is x minus 3i. The factor corresponding to this one is x plus 3i. Now, if we multiply this, we get the first one is here. So we start with the complex part. So here we have x squared minus 3i because this is complex conjugate product. Therefore, a minus b times a plus b is a squared minus b squared. So we have x squared minus 3i squared, and this is plus 9. Okay, therefore this will be x squared plus 9. And then if we distribute this one, if we again multiply this, we get x squared plus 2x squared plus 9x plus 18. And that's the polynomial with this information. So here we learn 2 things. One is, if you have the polynomial and we know at least one of the zeros, then we can write this one in a reduced form. We can write this function in a reduced form, which is basically this. And then we can continue factorizing this one. Okay, so by doing so, we can factorize any polynomial of any degree. Even if it is degree of 100, of course, it takes too much time, of course. But what I'm saying is it is possible by reducing it. Okay, we just reduce it. We go step by step. And again, the other one is, sorry. So we have the function, and we don't have the function, and but we have some information. And based on this information, we can construct the function. Okay, so that's the other way. That's the other question. Now, another theorem that is important here is the so-called rational zero theorem. And the rational zero theorem is, it says if f of x, which is given by this format, has integer coefficients and an is different from 0. So an is the first one, if this is different from 0. And if it has integer coefficients, okay, this coefficient, this an's, an minus 1, and so on, if they are integers, and if p over q written in lowest term, when you simplify this one, that means in a simplified form, is a rational zero of f, then p is a factor of the constant term a0, constant is this one, and q is the factor of the leading coefficient an, which is this one. Okay. Now, if we go back to this, for example, here we have this polynomial. So a0 is, or the leading coefficient is 2, and the constant coefficient is 273. So if we have p over q, and if we know this is a factor, if this is a zero of the polynomial, then this will be factor of the constant, and q will be factor of the leading coefficient. Okay, so basically that's what it's saying. Okay, so we can use this information to determine or to find zeros of a polynomial function. So for example, if we have h of x equals to 4x to the power of 4, 9x plus 9x cubed plus 2x minus 6. So here a sub n is 4, or the leading coefficient is 4, and p is negative 6. So if p over q is 0 of the polynomial function, then q is a factor of 4, and p will be a factor of negative 6. Now we can list the factors of each of them. For negative 6, the factors are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. All these are factors of negative 6. And factors of 4 are plus or minus 1, plus or minus 2, and plus or minus 4. So these are the possibilities. Now, the possible factors of this polynomial. Now we don't know if they are zeros or not, but the possible zeros of this polynomial, or rational zeros, I should say, the possible rational zeros will be p over q. Now we divide each of factor of negative 6 by each of factor of 4, but we don't need to repeat them. So plus or minus 1 divided by plus or minus 1 is still plus or minus 1 over 1. Plus or minus 2 divided by plus or minus 1, we have this, and so on. Okay. And then here we have, because we have 2 and 2, so 2 over 2, we have it here. But since 2 over 2 is 1, this basically means plus or minus 1, so, and we have it already here. Okay, therefore we cancel this one out. We don't need it because already it's written here. And similarly, plus or minus 6 over 2 is plus or minus 3, and that one is here. So we cancel that one out too. And plus or minus 6 over 4 and 2 over 4. 2 over 4 is 1/2, so we have it here. 6 over 4 is, where is it? 3 over 2. We have it here. Therefore, the repeated ones, they are redundant, so we cancel them out. We don't need them. And we are left with the possible rational zeros, which are plus or minus 1, plus or minus 2, plus or minus 3 over 2, plus or minus 6, plus or minus half, plus or minus 3 over 2, plus or minus 1 over 4, and plus or minus 3 over 4. Okay, Now let's use this example to see what this rational zero theorem can offer so that to help us find the zeros of a polynomial function. So consider this polynomial function, and well, we wanted to apply this rational zero theorem. So the first thing that we need to do is we need to figure out the factors of each of this a sub 0 and a sub n. For p, which is factors of -12, are these ones, and for q, which means factors of 2, are this ±1 and ±2. And if we divide each of the first numbers by the second one, then we get ±1, ±2, ±3, ±4, ±6, ±12. And then we divide each of them by this. Then most of them, they will be repetition. But then we have 1/2 and 3/2. The rest, 4/2 is already here. 6/2 is over here. 12/2 is here. Okay. Therefore, these are the possible factors, rational factors of this polynomial function. Now we can try each of them. Of course, it's time consuming, but we can try each and every or each of these possibilities to check whether they are rational zeros of the polynomial function or not. And to do so, we can use the synthetic division method and apply the factor theorem and of course the remainder theorem, and we can figure out whether these are factors zeros or not. So let's start with the first one. If I take C as 1, if I take the +1, then we have the coefficients 2, 3, -15, and -32 and -12. So using this, I got the remainder to be -54. Therefore, this is not a factor. Again, -1, it's not a factor because the remainder is 4. So we look for the one that gives us a remainder 0. And +2, it's not because the remainder is this number. And -2, it is a rational 0 because the remainder is 0. Okay. Therefore, -2 is a 0. And by the factor theorem, if -2 is 0, x plus 2 is a factor of f, or factor of f of x, okay? Factor of the function. Now, I can write the function in a reduced form, which means this factor times the remainder, the quotient is a polynomial function, another polynomial function with these coefficients. Therefore, this is here 2x cubed minus x squared minus 13x minus 6. So this is the reduced form of the polynomial function. Now the next step is we need to factorize this part, okay? And I will use the same thing, the same approach, and the p over q, as you can see, it has 2 and -6, which are exactly the same. That's what we have right here. Therefore, the numbers are still the same. They don't change. So using the same possible list of rational zeros, I will try again 1 and -1. So they are not. Again, they are not factors of this polynomial. Again, this is not, but this is a 0 of this polynomial again. So this is repeated twice. Therefore, -2 is a 0. So x plus 2 is again a factor. Therefore, I can write this one, x plus 2 times x plus 2. And the reduced one is a new polynomial with these coefficients. 2x squared minus 5x minus 3. And this time this is x plus 2 squared. And now the next is, again, we have to factorize this one. And factorizing this, since it's a quadratic now, we can just find two numbers whose product is -6 and the sum is -5. And those numbers will be positive x minus 6x minus 3. Okay, therefore this is 2x, x minus plus 1 minus 3, 2x plus 1. So we have 2x minus 3. Oh, wait. No. So from this one, we get just x, 2x plus 1. And from here, 3, 2x plus 1. Yeah. So it's x minus 3 and 2x plus 1. And that's what we have here. Therefore, we have factorized this polynomial. Okay. So the thing is, the idea here is we use the rational zero theorem. We list all the possible values or all the possible rational zeros, and we try if we can find one of them as a zero of the polynomial function. So we can use synthetic division, which is much more easier and time saving. And once we found one, we write the polynomial function in a reduced form, and then we factorize the next one. If it is quadratic, if it is simple, if it is easy, then you don't need to divide it. We can just factorize it using the quadratic methods, or we can use the quadratic formula. If it is not quadratic, if it is more than quadratic, then again we have to divide it to find another factor, and then by doing so we can finally arrive at the factorized form. Okay, and this is again another example, which is basically the same. So we list first P and Q. So the possible P and Q are this one. And as you can see, if you try each of them, there is no zero. What does that mean? Well, it means there is no rational zero. So it doesn't mean always a polynomial has, or all polynomials have rational zeros, right? The theorem says if P over Q is a rational zero, or if it is a zero. If it is a zero, then P is a factor of the leading, and then the constant, and Q is a factor of the leading coefficient, okay, if it exists. But it doesn't guarantee us that it always exists, okay? And this is similar way. Again, we can factorize this one. Okay. And the next is the fundamental theorem of algebra. And this theorem says if f of x is a polynomial of degree n greater or equal to 1 with complex coefficients, then f of x has at least one complex zero. Okay. If the degree is greater or equal to 1 with complex coefficient, then it has at least one complex zero. Now, to show this, we can consider this C to be a zero. Then we have x minus C1 times Q1 x, where this is a quotient. Again, since the quotient itself is a polynomial, we can write it as a reduced form, which is this way. And we can keep doing this, of course, till we simplify it or take it to the simplest form. And well, finally, this will be a constant. Okay, therefore, if the degree is greater or equal to 1, always there is at least one complex 0. Okay, it may or may not be real, but we always expect at least one complex 0. And remember, real numbers, they are also in complex numbers. Okay, they are complex numbers. They are included in complex, the set of complex numbers. And a linear factorization theorem, if we consider this polynomial, f of x, where n is greater than or equal to 1, the degree is greater or equal to 1, and the leading coefficient is not 0, then f of x can be written in this form. Okay, an times x minus c1 times x minus c2 and so on and so forth up to x minus cn. We can write this one. This can be written in this form as a product of n factors, where c1 up to cn are complex numbers. Okay, and again, the complex numbers includes even real and imaginary. Okay, and from here we go to the, as you can see now, what does it say? There are n linear factors x minus c, x minus c1 minus c2 minus up to cn. Okay, so here if we count this one, depending on the degree, the function has n linear factors. And in connection with this one, from here we can come to the number of zeros of a polynomial. So if we have a polynomial of degree n, which is when n is greater or equal to 1, then f of x has exactly n complex zeros. Okay, so if it is degree 2, we expect, or it has 2 complex zeros. If it is degree 10, it will have 10 complex zeros. Again, don't get confused by this complex 0. It means, it could mean real number or imaginary number. It includes both of them. For example, if we have f of x equals to x cubed, if we have this number, this function, n is 3, so we expect this polynomial to have 3 zeros. And those 3 zeros are 5 and 1 plus or equal to plus or minus root 5. Since each of them, since there are 3 different numbers as 0, then obviously the multiplicity is 1. Okay, and again we have another polynomial here. N is 4, which means the degree of the polynomial is 4. So this polynomial has 4 zeros, and the zeros are 1 over 3 and negative 4, each of with multiplicity 1, and then 2 with multiplicity 2. So if you look at these numbers, they are 3. But since this guy has multiplicity 2, which means we have 2 comma 2, we have 2 2's as zeros of the polynomial. So in total, we have this. Okay, but normally we don't write, if it is the same number, we write 2 and we say it has multiplicity 2. So these are the number of zeros of a polynomial and linear factorization theorem. And the next is the conjugate zero theorem. And this says, if we have a function or a polynomial with real coefficients, and if a plus bi, where bi is different from 0, is a 0 of f of x. So remember this function, this expression, this is a complex number or an imaginary number. Then its conjugate a minus bi is also a 0 of f of x. Okay, so just simple example. If we have 2 minus or plus I, let's say, if this is a 0 of a polynomial, then the complex conjugate of this one, 2 minus I, is also a 0 of the polynomial. So this is very helpful. Once you know this complex number or this number is a 0, then we know the the complex conjugate is also a 0. So it's saving some time. For example, if we consider this example, this function, the zeros of this function are plus or minus root 13 and plus or minus I, each with multiplicity 1, of course. And if we consider this polynomial again, so and we know 4 minus I is a 0. So now remember, this one is cube degree 3, and from degree 3 we expect 3 zeros. Okay, here we have 1 0, which is 4 plus I, and by the conjugate zero theorem, if 4 plus I is a 0, then 4 minus I is also a 0. Okay, 4 minus I is a 0 of the polynomial function. Therefore, out of the 3 zeros, we know 2 of them. One is this, another one is this one. So how many are left? Well, it's just 1 left. Now, find the zeros of the function, f of x. Now we are left with 1 to find. And how do we find that one? So to do so, what we do is we divide this function by 4 minus I, and we get by 4 minus I, and then by 4 plus I, and then by 4 minus I. So since we have 2 of them, we divide the polynomial by this. Okay, in both cases, the remainder is 0. Okay, and now we multiply this 2. We multiply this 2 because this 2, if this is a 0, then x minus 4 minus I and x plus 4 minus 4 plus I are factors, both of them. So we multiply this. Okay. So basically what it means is we can write this reduced form of this function since already we know 2 of the factors. The first one is this, second one is this, and the third one is the one that we don't know, which is q of x. So we multiply these 2 first because we know them, and then we divide f of x by this one to find q of x. Therefore, f of x is product of this, which is okay. Yeah. So yeah. So the first one is here. The second one is here, and the remaining is 3x minus 4, which is this one. Okay. Okay. And then the second question is factor f of x as a product of linear factors. So we can write this one as a product of linear factors. Well, it's just this one, x minus 4 plus I, x minus 4 minus I, 3x minus 4. So we have f of x as a product of 3 linear factors. And then solve the equation f of x equals to 0. Well, we know once it's factorized, we have x equals 4 plus I, x equals 4 minus I, which is from here, and then x equals to 4 over 3, which is, so these are the zeros of the function f of x. Okay, now, given a polynomial of degree 3, well, we wanted to write a polynomial of degree 3 with integer coefficients with 0, 6i, and 4 over 5. So for a degree 3, for a polynomial of degree 3, we know there are 3 zeros, and 2 are given. 6i and 4/5 are given. Since this is a 0, then its conjugate, which is minus 6i, is also a 0 of the polynomial. Therefore, that means we know 3 of the zeros. Okay, and the corresponding factors or linear factors are x minus 6i, x plus 6i, and x minus 4/5. Okay, therefore, by multiplying these three factors, and of course, we always write a at the front because does it say anything? No, it doesn't say. So we put a here because we don't know what that number is. And then once we multiply this, we get x cubed minus this number. And by rewriting this, we get this number. Oops. Okay, by rewriting this one, we get this. So we can keep this, we can take a to be 5. The reason why we take a5 is just to make it easy, just for simplification, so that we can cancel 5 out. We have 5 as a denominator, and we wanted to remove that one. And the reason is because it has integer coefficients. So to make them integers, to make the coefficients integers, we have to multiply by the we have to multiply each of them by the denominator. Okay, and the denominator is 5, so we get this polynomial. So this polynomial has degree 3, or it's degree 3, and each of the coefficients are integers, and of course it has 3 factors and linear factors and 3 zeros. Okay. All right, so I think I will stop right here, and we will continue with this in the next lecture. So yeah, see you in the next lecture.